is that a is root of polynomial p of x if and only if when p of x can be divided by a binomial x minus a with a zero remainder, or our number r is equal to 0. So these two facts are equivalent. When a is the root of our polynomial, then our polynomial can be divided by x minus a, and remainder will be 0. Let's prove our theorem. This can be done very easily. When we divide our polynomial p of x by a binomial x minus a, we have a representation p of x is equal to x minus a times some polynomial q of x plus a remainder r. And when we insert instead of x number a, then we have this. And since a minus a is equal to 0, this member will be 0. And that's why p of a is equal to r. And when our r is equal to 0, then we have p of a is equal to 0, or equivalently, a is the root of our polynomial. That's why if we want to prove to this side, when a is the root of our polynomial p of x, or this, we must have r equal to 0. Remainder must be 0. And opposite, when remainder is equal to 0, then we have p at the point a is equal to 0, or a is the root of our polynomial. So this was the proof of our result. Our next example, assume we have a polynomial p of x is equal to x to the power 3 plus 5x squared minus 18. This polynomial can be divided by a binomial x plus 3. And this x plus 3 can be written as x minus 3. And let's divide our polynomial by this binomial. And we know from Bezout theorem that in this case a remainder will be equal to p at the point minus 3. And if we calculate, we will have minus 3 to the power 3 plus 5 times minus 3 squared minus 18, which is equal to minus 27 plus 5 times 9 minus 18. This is equal to 0. And since remainder is equal to 0, it means that number minus 3 is the root. This is a root of polynomial p of x. Another very important result that follows from Bezout theorem is that assume we have a polynomial p of x, and it has a, let's give an example. Assume we have a polynomial x to the power 2, x squared minus 4x plus 3. And first of all, this result is formulated like coefficients. Here we have 1. Coefficients of our polynomial must be integer, and any integer root of our polynomial must divide our free member coefficient with that corresponds to x to the power 0. This is 1. And we always avoid writing this, but we look at the free coefficient. This is called free member or free coefficient of our polynomial. And any integer root of our polynomial must divide our, in this case, number 3. That's why if we have integer root of our polynomial, these roots can be plus or minus 1, because plus and minus 1 divide our number plus 3. And it can be plus or minus 3. And we can search the root of our polynomial, of our equation x squared minus 4x plus 3 equal to 0. Among these numbers, these 4 numbers, plus minus 1 and plus minus 3. Of course, we assume that roots of our equation are integer. Why is that? Because when we have, for example, 2 roots of our polynomial, of our equation, p of x must be equal to x minus a times x minus b. And in this case, and a and b are roots of our equation, because when we insert instead of x number a, we will have 0, because this factor will be 0. And again, if we insert instead of x number b, we also will have a 0, because this factor will be 0. So a and b are roots of our equation. And since we can write our polynomial as, let's perform multiplication, it will be x squared minus bx minus ax plus ab. Or this can be written as x squared minus x, or plus ab. And this free member of our polynomial is equal to ab. Assume this is n. So our n is equal to ab, and roots of our polynomial a and b must divide our number n. That's why, let's repeat it again, integer roots of our polynomial must divide our free member. Let's give one more example in this case. Let's prove that let's search the roots of our polynomial among these numbers. Let's give an example for this result. Example for polynomial p of x equal to x squared minus 4x plus 3. Let's search the roots of our polynomial from result that follows from Bezout theorem. We know that we have to search roots, integer roots of our equation among numbers plus minus 1 and plus minus 3. And if we insert instead of our variable x number 1, we will have 1 squared minus 4 times 1 plus 3. It will be 0. That's why number 1 is the root of our equation. And we can divide now our polynomial x minus x squared minus 4x plus 3. We can divide this by x minus 1 because 1 is the root of our polynomial. And when we perform a division, let's perform our division very quickly. We have a cancellation here. And we will have here minus 3x plus 3 minus 3 minus 3x plus 3. And when we perform a subtraction, we will have a 0. So when we divided our polynomial by this binomial divisor, we had a quotient. In other words, our polynomial p of x is equal to x minus 1 times x minus 3 plus a remainder which is equal to 0. And that's why we can found the second root of our equation. And since from the result previously given, we have that since x minus 3 divides our polynomial, that's why number 3 is the second root of our polynomial, of our equation. It was everything for today. Like us and subscribe, and good luck.